So we're continuing with pushdown automata, context-free grammars. We defined pushdown automata as a finite automata with a stack. It has all the same components of a finite automata, set of states, transition functions, stack, alphabet. The only thing about different pushdown automata has a stack, a finite automata doesn't. So you can think about a finite automata as a pushdown automata without a stack. Or conversely, a pushdown automata is a finite automata with a stack. So a transition function can depend on what's on the stack. And at every transition, it looks at the state that it's in, an input character, and the content of the top character of the stack, and then it makes a transition accordingly. Non-determinism is essential because there are languages that are context-free that cannot be recognized by any deterministic pushdown automata, but they can be recognized by non-deterministic ones. So non-determinism is built into the definition of pushdown automata, and we mentioned that pushdown automata and context-free grammars are characterizing the same class of languages, namely the context-free languages. And also we proved a bunch of closure properties of context-free languages last time. We proved that context-free languages are closed under union, clean closure, intersection with regular languages, but they're not closed under intersection complementation. That follows from de Morgan's law and the properties of set identity regarding unions and intersections and complements. Decidable properties of pushdown automata on context-free grammars include whether the language of them is empty or not, whether a language of each is finite or not, infinite, and whether a string is in a language or not. That's the problem of parsing, actually. And for extra credit, we asked to prove these. Minimizing PDAs is undecidable. There's no algorithm for it. Determining whether two PDAs are equivalent, that is, whether they recognize the same language, that's also undecidable. Whether a language or a context-free grammar is minimal or ambiguous or inherently ambiguous, these are all undecidable properties. So complexity and undecidability starts to rear its head right here at this level of computational power of the PDA kind of capability. Whether the intersection of two context-free grammars or languages is empty or not, that's also undecidable. And again, for extra credit, you can take deeper dive into these topics. We argue that two-way PDAs are more powerful. You can recognize using a two-way PDA, for example, 0 to the n, 1 to the n, 2 to the n. That's not context-free, but it is decidable. It's just not doable with a PDA. Two-stack PDAs are more powerful than one-stack PDAs. A two-stack PDA can recognize WW, which is not context-free, or 0 to the n, 1 to the n, 2 to the n, which is, again, not context-free. In fact, two stacks are equivalent to a Turing tape. One of the problems on the problem sets states that. A QPDA also more powerful than a PDA. A QPDA is as powerful as a Turing machine. Two-head PDAs are more powerful than one-head PDA, but not quite as powerful as a Turing machine. And non-determinism does increase the power. So we proved using the pumping argument that certain languages are not regular. So for example, 0 to the n, 1 to the n, it's not regular, because every regular language has a pump in it, a short string, no longer than the number of states of a finite automata that recognizes it, such that when you pump it up, you remain in the language. So four nested quantifiers, existential and universal, basically say it. But the idea is that by the pigeonhole principle, some state must recur. And whatever led you to that state, that from there you got to a final state, whatever that loop was around that state that recurred by the pigeonhole principle, you can pump that up as many times as you want. And all the resulting strings for all powers of that pump must remain in a language. So it's a property of regular languages. So let me ask you a subtle question about this. So this says that for every large enough string in the regular language, there is a pump that gives you an infinite family of strings that must also be in the regular language. How many get that? Okay. Just three of you? All right, let me repeat. The pumping lemma says that for every string long enough in the regular language, you can pump it up to arbitrary power. There is some section in that string. I'm not saying where it is, but there is some section of that string that when you pump up to arbitrary powers, leaves you in the language with respect to all these larger pumped up strings. How many get that? Okay. Here's the subtle question. Is it also conversely true the other way around? That every large enough string in the language is the result of pumping up some smaller string? How many say that's true also? How many say it's not true? Okay, good. Why not?
In that case, you take that as an test for regularity or non-determinism, but we don't. So just to intuit that should be.
Yeah, it's not true because there are strings that are arbitrarily long that contain not just no large pumps and contains not even any small pumps. There are strings that are arbitrarily long and contain no cubed terms. No substring will repeat 3 times in a row. None. In that long, arbitrarily long string. Okay. So they're called cube-free strings. And Sigmastar has many, many cube-free strings. And, there's many context-free languages, including Sigmastar, that have cube-free strings in them. So, and those are not pumpable from lower strings. So you can have a string of size of Googleplex where no substring, however small, however large, recurs 3 times in a row, one after the other. Never mind arbitrary number of times. Okay, how many understand that statement? If that seems fuzzy to you or not believable even, and it seems a little counterintuitive, why is that true? Think about numbers, integers. Every natural number is the product of primes. Right? It's the product of smaller numbers. And the pumping theorem for numbers would be of this form, or could be of this form. Any large enough number contains a factor that if you pump it up, if you raise it to some exponent, arbitrary number of times, you'll end up with another integer, another natural number that's also in a set of integers. So every integer is pumped up using some exponentiation of one of its factors. How many believe that? Good. That's obvious. If nothing else, take the number itself. But it's not true that every integer, however large, was the result of pumping up some smaller integer, raising that to a power. How many understand that? And prove that to me. Prime numbers. Prime numbers. They're not the result of raising anything smaller to a power. So what I just got through telling you a minute ago is that there are prime strings. Prime strings. Strings that are not obtainable by concatenating or raising to power any small subsection of themselves or any other string smaller than them. They're not obtainable by repeated concatenations of anything, even if you allow arbitrary ends on them, like U and V. There are strings that don't have any pumps whatsoever, no powers of smaller strings in them. They're prime strings. How many understand that now? Okay, that's good. We picked up a few more people. Any questions about that? There's problem set questions that relate to what I just said about prime strings. Strings are cube-free, for example. They don't even have a third power of anything, never mind higher powers. It's hard to come up with a square-free string. In fact, arbitrarily large square-free strings don't exist. You can show that, right? How would you show it? So let's say the alphabet is 0, 1, and you try to come up with a square-free string. So you can start with an A, and then you can't have an A because that'll be a square. It'll be A squared. So then you put a B. You can't put a B because that'll be now a B squared in there, so you have to put an A again. Now you can't put an A again because it'll be A squared right there, so you must put a B, but now you have AB squared. And that's where it ends. So you cannot have arbitrarily large square-free strings. How many get that? But you can have arbitrarily large cube-free strings. If you have a third character to work with, a C, keep throwing in the C and then go back to A's and B's and more C's, and such that no substring in there will be cubed anywhere. It's interesting. Try to prove that for extra credit. Any questions about that? There was a question, yeah. So a prime number cannot be decomposed into factors other than one in itself.
Yes. Right? So if you have try to decompose them using those smaller numbers,
So it's not about the subscripts. A prime number is atomic. It's not decomposable into anything, right? So it doesn't matter what you call it, what you call the so-called factors. There are no factors there other than one in itself, right? So I'm not sure what you mean by subscript.
For example, if we decompose 10, we'll have.
But 10 is not prime.
I say give an example. I mean representation of 10. So you get 2 to the superscript of 1 and 5 of superscript of 1.
Yeah.
And then when we decompose 7, we'll represent using a 1 with superscript 1 and 7, superscript 1 and 5, anything between 2 to 6 will be 0.
Oh, I see. So but those are not real factors. Those are just ones.
Something that we represent those prime numbers as like the b here being 0. The length of b here.
But this is not about representation. It's what the value is. So you're kind of focusing on the representation. So you want to represent 1 as 6 to the 0, and 5 to the 0, and 7 to the 0, and 4 to the 0. But that's just a representation trick, right? Those factors aren't really there. You see? So what I'm saying is, regardless of representation, there are no more factors in there, right? Which is a different fact, right? So it's not about, this business is not about representation. It's about what the value of these objects are and what it isn't, right? Yeah.
When you actually say arbitrary long string, what do you
Size of Googleplex, size of Googleplex factorial, really long. However long you want. By arbitrary long, I mean the length of any integer, however large. No end to the length. Not infinite, just arbitrarily large, like the integers are, arbitrarily large. But no integer is an infinity in of itself. Question goes. Yeah.
For a language, or I guess, for an arbitrary long string that's in a language, does that say anything about the number of states? So, it's not accepts that.
Good. So if you have arbitrary long strings in a language, does the automata have to be bigger and bigger and bigger to accept larger and larger strings? How many say yeah? How many say no? Good. Why not? You can have, one state automata accepts Sigmastar.
Right.
So arbitrary long strings get accepted by a very small finite automata, right? So that they're not core.
Even these strings with no repetition.
Well, you tell me. Does Sigmastar contain strings with no repetition? Of course. It contains every string. It contains Shakespeare's Hamlet as a string. It contains our textbook as a string. It contains next week's Wall Street Journal paper, complete cover to cover, with all the stock prices of next week as a string. Everything is there. And yet, one state finite automata accepts all of those. So don't confuse what a finite automata can do with what it can't do. So the power of an algorithm or a computer in general, or a finite automata, or any computation, is not just the answers that it gives you, but the answers that it doesn't give you. It's not only what it can accept, but also what it should reject and does reject. So if I have a clock that stopped, if that clock on the wall was a dead clock and it stopped, it'll show me the correct time twice a day. And over 700 times a year, it'll show me the correct time. In fact, it'll show me the correct time infinitely often. Right? A dead clock. But the problem is, it also shows me the wrong time infinitely often too. And that completely negates its usefulness. So a clock shouldn't just show you the right time infinitely often. It should not show you the wrong time infinitely often. It's very, very important. It's hard to overemphasize that. Let me give you another example. In a court of law, when they swear you as a witness, they don't just say, tell me the truth. It's a lot more involved than that. If you just say, tell the truth, and you go and start to testify in a court of law under oath. What's the problem with that scenario? And you say, I swear to tell the truth. And then you start talking. What's the problem here? You can also tell lies along with the truth. You told the truth and you said you would. So you're doing what they told you to do, to tell the truth. But you're also telling lies in between the truth. And that makes your whole testimony pointless and useless. And it doesn't even stop there. So you're telling the truth and you're telling only the truth. What's wrong with that scenario? You're not telling the whole truth. So you're saying parts of the truth that you cherry pick and choose, but not the whole story. And that can really change your testimony. Right? You could omit the part where you killed somebody, even though you said everything true before and after that. That's no good. Okay? You're not lying, you're just not telling the whole truth. So you need to tell the truth. A. B. You need to tell the whole truth. C. You need to tell nothing but the truth. And these are three separate things. Okay. And I hope you understand the subtlety and the generality of this scenario. So a finite automata, any automata, a Turing machine, a PDA, must accept everything that's in the language, but that's not enough. It must also what? Reject everything that's not in the language. And sometimes that's harder than the first part. How do you get all this? Very important. That's why sometimes the complement of a language is much more hard to recognize than the language itself. Because telling what's not in there is harder than telling what is in there. In a provable way, actually. Let me give you another example that's even more dramatic. Imagine you have a library that has every single string in the universe as a book. So Shakespeare's Hamlet is there, and one of the it's an infinite shelf. Starts here, but goes on to like Infinite Hotel. Every book is on this shelf. Every possible book. So Shakespeare's Hamlet is there, but so is Pinocchio, and so is the Wall Street Journal of next week. So is some physics textbook from the 23rd century. So is the movie Rocky number 57. Probably will come out eventually, and so on and so on. Every possible single book is there. So it has infinite knowledge in some sense, right? Every possible thing is there. What's the problem with this reasoning or this scenario? How useful is this library? How much information does it contain really? And how would you look something up in this library? Infinite shelf. So the smallest books are first, one character books, not very useful, and two character books. And so they're sorted by size, by number of characters, and then within size by lexicographic order. That's one big shelf. In other words, this shelf is Sigmastar. Right? So let's say you had access to this library. You can start marching down this shelf looking for books. And how useful is that? How much information is in this library? All the information in the universe? In some sense, yeah, right? But what's really the information content of this library? Answer me this. If you had to look up a book in this library, what would the card catalog, the index of this library would look like? If you were to look at a particular book, like the next issue of Superman comic, whatever that is, what would you have to know to look that up in this library that does contain it, sure enough? You need to know exactly the book that you're looking for. Because Shakespeare's Hamlet is there. So could you search for all sorts of blockbuster movie scripts that nobody's ever thought of, but they're all there, so if you find them, you'll be a trillionaire because you'll have all these great stories on your hand? No. Why not? They are there. What stops you from finding them? Shakespeare's Hamlet is there, but so is Shakespeare's Hamlet with one character changed from an A to a B. Shakespeare's Hamlet with one character mutation is there too. How could you tell the difference? You have to know that mutation. If you know that mutation, you don't need to look it up. So the card catalog for this library looks like what? By the way, don't want to be presumptuous. What is a card catalog? This is the internet age. How many have been to a library, physically entered a library in the last year, say? The last month? Okay, good for you. I'm impressed. Some people haven't entered a library in years. Some universities are doing away with their libraries even in today's age, right? How many know what a card catalog is for a library? Okay, maybe that's the problem. You go into a library, we used to have these, shelves full of little index cards, 3x5 cards that you look things up and then it tells you which shelf it's in. You go to the shelf, you grab the book. How many even know what I'm talking about? Okay. What was the card catalog for this infinite library of infinite number of books containing Sigmastar? What does that card catalog look like for this library? Itself. How many get that? Because every book in the universe is there. So in order to find a book, all the variations of that book are there too. You have to know exactly which book you're looking for in order to find it. But if you know what you're looking for, you don't need to find it. You already know it. So the information content of this library is what in information theoretic sense? Zero. The library has zero information in it. How many understand that? Even though it seems like it has all the universe's knowledge in it, which in some sense it does that too. So a library is not just useful for the books that are there. A library is useful and valuable because of the books that are not there as well. That's very important. Every single possible book in the universe was there. The library will be completely useless to you. And information theoretical will have zero knowledge, zero information. Any questions about that? This is a subtle concept, kind of almost a philosophical concept, except it's mathematically true. The point is, well, there's many points. One of the points is a language is not just complicated by what's inside that language. It's also very complicated because of what is not inside that language. Sigmastar has everything in it. It's a trivial language. But everything is there. However complicated the string is, it's there. So having more and more and more things in there doesn't necessarily make it more and more complicated. It could make it trivial, in fact. Right? So keep that in mind. It's an important concept. Any other thoughts or questions about any of this? Okay, so